Welcome and thank you for joining. In this lesson, we'll explore how to use the second derivative of a function to predict the shape of its graph, or the concavity. Concavity indicates the direction of the bending of a curve. There are two types of concavity that we study. The first one is what we call concave up, and that looks like a cup, and concave down, which looks like a frown. So for short, we write cup for concave up and CD for concave down. Now, as you can see in here, in a concave up shape, the graph of the derivative will be above its tangents. And in a concave down shape, the graph will be below the tangents drawn to it. So, how does the second derivative help us determine concavity of a function? For this, we will have to explore the pattern in the values of the first derivative. As you can see in here, when reading the graph from left to right, the slope of the tangent starts with a negative, so a negative slope. It becomes 0 and then changes to positive. So since the slope of the tangent, which is also called the derivative of the function, that means the same thing, goes from negative to 0 to positive, it means that the slope of the tangent is increasing, or the derivative is increasing throughout the concave up bend. Now, an increasing value of the first derivative means that the first derivative has a positive rate of change. So, in other words, we're going to say that the rate of change of f prime x, which is basically the derivative of f prime x, or even better, the second derivative of f of x, will have a positive value because, again, the derivative is increasing. So derivative has positive rate of change. Or the rate of change of f prime x will be positive. So that's why we say that the second derivative in a concave up shape will be positive. So f second x is positive. And the way I like to memorize this or remember this is by thinking that since this looks like a cup, there is a positive quantity inside the cup. Now, similarly, in a concave down shape, we study the sign of the slope of the tangent, or the derivative. And as you can see here, the slope of the tangent starts with a positive value, becomes 0, and then negative, which tells us that the first derivative is decreasing in value, so positive to 0 to negative. So in other words, we're going to say that the first derivative will have a negative rate of change. So the rate of change of f prime of x, which is basically f second x, will be negative. So f second x is negative. And again, in a similar way, I remember this connection by thinking that since the cup is down, then it cannot hold anything inside it. So f second x is negative. Now, as you can see, when the graph has a concave up shape, it will also host the minimum point on the function, or on the location where the concave up shape is located. So, in other words, we're going to say that the lowest point in here will, so in a concave up shape, we have the lowest point, or the local or absolute sometimes minimum point on the graph of the function. Whereas in a concave down shape, we have the highest point in here, which will mark the point where the slope of the tangent is 0, and we'll say that it will mark the highest point on the graph of the function, or the local or absolute, sometimes maximum value of the function. Now, the point where the graph changes concavity from concave up to concave down is what we call the point of inflection. So, for example, if we had the graph of the function going concave up, connected to the graph of some function that is going concave down. And here I'm going to do something kind of interesting. So I'm just going to grab this, bring them close to each other. So the point where concavity changes, and that is because, always remember, f second goes from positive to negative. Just like for any quantity that goes from positive to negative, it must pass through the point where the derivative is 0. So what that means is that at the point where concave up meets concave down, then the second derivative would be equal to 0. This is what we call the inflection point. So to find the inflection point, or the point of inflection on the graph of a function, we find the second derivative and determine the value of x for which the second derivative is 0. So based on all our observations, we're going to say that in order to define whether a critical point, which is located to the point where the first derivative equals 0, will mark either a min or a max if and only if at the critical point, so it would be a minimum if at the critical point the second derivative is positive, and it will be a maximum if the second derivative is negative. So to find the inflection points, we set the second derivative equal to 0, and then we check for change in concavity. In some occasions, we may have the second derivative equal to 0, but the concavity will not change. And if the concavity is not changing sign, it means that the inflection point doesn't exist, even if the second derivative is equal to 0. Now, we are going to take a look at a couple of examples and see how we use the second derivative to determine the shape of the graph. Now, in the first example, we have to show that f of x equals x squared has no points of inflection. So we know that points of inflection means that the second derivative has to be 0 at some value of x. So we'll start off by finding the first derivative. In this case, would be 2x, and then the second derivative, which would be equal to the derivative of the first. Derivative of 2x is 2. So this is equal to a constant value, which means that there are no values of x that can make this equal to 0. So this is always going to be a different than 0 number. And we know that the graph of this function will be the graph of a parabola with a vertex at 0, 0. And we'll say that since there are no points of inflection and the second derivative will always be positive, it means that the graph of this function should be in a concave up shape at any point throughout its domain. And not only that, but because the turning point, or the point where the first derivative is equal to 0 at x equals 0, is hosted in a concave up shape, then this point, this critical point, will mark a minimum. Now let's take a look at another example. So here we have to determine concavity, inflection points, and then check with the graph. So we're going to start off with finding the derivative. Dy dx equals 3x squared minus 6x minus 9. So we need to determine concavity, which means that we need to determine the second derivative now. So that's 6x minus 6. So to study the sign of the second derivative, we'll have to make this equal to 0. So we have to find the 0 of it first, which happens at x equals 1. So at x equals 1, we have a key value, which can turn out to be a point of inflection. So we are going to build the chart for the second derivative. So here goes the number line from negative to positive infinity. And here goes the sign of the second derivative, which is in the form 6x minus 6. It has a key value right at 1. Based on the sign of the derivative, then we can determine the behavior of function y, or the shape, or the concavity of y. So at x equals 1, the derivative will be 0. For x values less than 1, the derivative is negative. Remember, this is a line that goes up because positive slope, which means it starts negative, continues positive. And that tells us that the graph of this function will start with a concave down shape and then continue with a concave up shape. Since at x equals 1, the concavity changed from up to down, from down to up to be more precise, then therefore this would be a point of inflection. So we're going to say that there is a point of inflection at x equals 1 and y equal to 1 cubed minus 3 times 1 squared minus 9 times 1 plus 15, which equals 1 minus 3, negative 2, negative 12, and then plus 15, 3. So therefore, we're going to say negative 3, negative 2, that's a 4 actually. So negative 2 minus 9, negative 11, plus 15, 4. So the point of inflection will be at x equals 1 and y equals 4. Now, if you want to check with the graph, obviously we can just draw the graph of this function on Desmos, x cubed minus 3x squared. Y equals x to the power of 3 minus, we said 3x to the power of 2, minus 9x plus 15, I think. Let me double check. Minus 9x plus 15, that is correct. So let's take a look at the graph of this function. And as you can see in here, let me just take a picture so we can write notes on it. It's always useful. There we go. Almost there. So as you can see in here, the graph of this function will change concavity at this point of inflection right here. So we have a concave down shape that is following with a concave up. Well, I hope this made sense. Thank you for watching, and in the next part of this lesson, we'll continue with the second derivative test. Bye for now.